Okay, in this video, we're going to talk about how oxygen is carried in the blood and how you get oxygen onto hemoglobin and how you ultimately get it off so you can use it. Oxygen is carried in the blood in two main ways. As described by this equation, which just tells you the content of oxygen in arterial blood, that's what the little a means. So the C, big C means content, little a means arterial. As described by this equation, oxygen is transported in the blood primarily and as bound to hemoglobin. That's what your red blood cells are primarily for, and also dissolved in the blood, specifically in the plasma. So 98% is going to be bound to hemoglobin in your arterial blood. So that's what this is. If we take a blood sample and centrifuge it down, you split up the blood into three parts: your red blood cells, your white blood cells and platelets, and then the plasma. About 98% of that oxygen is going to be bound to hemoglobin, which is in the red blood cells, and about 2% is dissolved in the plasma. So, one of the tricks here, though, is that it's actually the oxygen that's dissolved in the plasma is what's available to give to tissues. And we only have 2% of our oxygen actually readily available to distribute. So most of it is in this hemoglobin savings account, where once the levels of oxygen in the plasma get low enough, whatever oxygen is in the red blood cells on the hemoglobin will gradually diffuse off of the hemoglobin and go into the plasma so that you can use it and deliver it to the tissues. So red blood cells and the hemoglobin are kind of like our savings or storage for oxygen, and the plasma is actually where we spend the oxygen and diffuse it into other tissues. So what dictates how much is bound to hemoglobin and how much is dissolved in the plasma? Well, the biggest thing in determining how much is dissolved in the plasma and how much is bound actually is this pressure of oxygen in the blood. Here we're looking at the content of oxygen in arterial blood, C little AO2. So we're going to use the pressure of oxygen in the arterial blood, or P little AO2. If we were interested in the vein, we would look at the pressure of oxygen in the vein, and that would change all these different things. So the pressure of oxygen in the arterial blood will first directly influence how much is dissolved in the plasma. For every 1 millimeter of mercury of oxygen pressure we have in the blood, we get about 0.003 milliliters of oxygen dissolved in 100 milliliters of blood. That's not a lot. Um, so, so let me explain one more thing. I just said that we would get 0.003 milliliters of oxygen per 100 milliliters of blood. So most of the time when you're talking about how much concentration of something there is in blood, it's measured per deciliter of blood or per 100 milliliters of blood, same thing. So this, just imagine that this vial over here is 100 milliliters of blood. And so this CaO2 is going to tell us how much oxygen there is in that vial of blood if it's 100 milliliters. Okay, so that's what the deciliter or 100 milliliters is, 1 deciliter or 100 milliliters. So the pressure of oxygen strongly influences how much is dissolved in the blood. The higher the pressure, the more oxygen you get dissolved in the plasma. But this really isn't a whole lot. You consume, if you're doing intense exercise, you're consuming 3 liters of oxygen every minute. And here we get about 0.003 milliliters of oxygen dissolved in the blood for every millimeter of mercury. So it's not a lot, right? So most of the oxygen that we're going to actually carry and then ultimately use is first stored bound to hemoglobin. And how does that relate to the pressure of oxygen? Well, first of all, as we're going to see in a second, the pressure of oxygen dictates how much oxygen is actually bound to hemoglobin. So if we have a low pressure of oxygen, so let's say we have low oxygen here in the plasma, what's going to happen is that any oxygen we have stored on the hemoglobin, or some of it, will dissolve off and come in and restore our plasma levels so that we can have oxygen readily available. So you can imagine if we have a high PO2, this won't have to happen. A high PO2 will result in a lot of oxygen being bound to hemoglobin and a lot of oxygen delivered down to the muscle. Now, another thing that's going to influence how much oxygen is transported is the concentration of hemoglobin, how much red blood cells you have in the blood, essentially. So if we look at this diagram here, down here, a person with a high concentration of hemoglobin might have their red blood cells going all the way up to here. So it's somewhere around 60%. A person with a low concentration, it might tap out really low, somewhere around 30% or so. That would be a case of anemia. When a person lacks red blood cells, that's anemia and they can't transport oxygen. Now, while we're talking about it, if you have really high levels of red blood cells, you might think, well, that's going to be fantastic. I can carry a lot of oxygen, but it comes at the detriment that now your blood gets very thick and viscous and you can't transport the blood very easily. And that has its own problems. So generally somewhere around 50% of your blood volume being red blood cells is around the optimum, or where most of us are at. So let's now explore this relationship. How does PaO2, the pressure of oxygen, influence hemoglobin saturation? You can look at these little labels later if you pause it. So looking at the relationship between the pressure of oxygen and percent saturation. So normally a heme molecule can bind 4 oxygens. And if you have high pressure of oxygen, you'll have 100% of those spots on your hemoglobins bound. If you have a low pressure of oxygen, no oxygen, you have none of them bound, right? So let's assume for a second that the relationship between pressure of oxygen and saturation was linear, like this. So that for every 1% increase in pressure, you get a 1% increase in oxygen saturation of hemoglobin. What that would mean is that when you're at sea level at let's say a PO2 at San Diego, would be a PO2 in your blood is probably about 100 millimeters of mercury, you'd be 100% saturated. And here in Provo, our PO2 in the blood is maybe 90. So that means we would take a hit, right? How saturated our blood would be in Provo would go down by about 10% or 15%, depending on exactly where you're at. So you'd see pretty marked or big impairments in oxygen delivery going from San Diego to Provo. But we see differences for sure, but not nearly that large, where we're seeing 10 to 20% changes. And the reason for that is because the relationship or the affinity of oxygen for hemoglobin, while it's influenced by the PO2, that relationship is not linear. In fact, as I'll show you in a second, it goes something like this. So that going from Provo to sea level or vice versa, it will decrease your saturation of hemoglobin by about 5%, 3%, depending on the person. So not a huge difference. This nonlinear relationship on this end makes us able to cope with going to higher altitudes. We don't have to live at sea level where the pressure of oxygen is higher. We can go up into the mountains and still be okay. We won't be as good, but we're still okay. Whereas if we had this linear relationship, going to Provo would really impair your athletic performance, right? Or your ability just to live. Our saturation would be much lower than it actually is. So fortunately for us, it's not a linear relationship. So let's look at this. This is the hemoglobin saturation curve, or the oxyhemoglobin saturation curve. And it shows how saturated your hemoglobin will be with oxygen at different pressures. So we've already said that at a pressure of about 100 millimeters of mercury, which is standard in the blood at sea level, arterial blood, you'll be about 100% saturated. And if you have no oxygen, obviously the hemoglobin will not be saturated. You'll be way down there. The cool thing is that if you're about if you have a pressure of, I think it's 27, pressure of 27 millimeters of mercury, really low, your hemoglobin will be 50% saturated. And so we get this curve where we get 50% saturated with hemoglobin with oxygen at a really low pressure. And then it starts to taper off after that. Okay. So I'd already introduced this idea of sea level versus Provo, where sea level, the pressure of oxygen in the blood is about 100, and Provo is somewhere around 80 or 90. And so that would reduce how much oxygen is carried in the blood or bound to hemoglobin. But it's not just that. The pressure of oxygen in our blood varies depending on where in the system you are. If you're in the arteries of the lung, so this is what it's, so blood that's come out of the lung and is in the arterial blood where it's oxygenated, the pressure of oxygen is going to be really high. If you are down at the level of a capillary of an extremely active muscle, you'll be down around 20, right? So you're consuming all this oxygen, the pressure of oxygen is going to be really low. So what that means is that at the lungs, where we have these really high pressures of oxygen because it's basically ambient air, we're going to load a bunch of oxygen onto the hemoglobin. But when we get down to the active muscles that are consuming the oxygen, like super active, so it'll have about a pressure of 20 millimeters of mercury. Why is it that low? Because the muscle's consuming the oxygen, okay? So because it's consuming it, the pressure of oxygen in the blood at the level of the active muscle is really low, so we have less bound to hemoglobin, or hemoglobin's not going to bind as much. Now, how could that be beneficial? Just think about it. We don't want the oxygen bound to hemoglobin. We want it dissolved off of the hemoglobin going into the muscle. So by having a low pressure down here at the level of the muscle, that's going to favor offloading the oxygen from the hemoglobin and delivering it to the muscle. Now, you might have noticed right here, it says the veins at rest are about a pressure of 40 millimeters of mercury. Why is that higher than the muscle if the veins drain the muscle? Well, first of all, it's at rest, right? And here at this level at 20, I'm talking about active muscle. The second thing is when you look at the veins are draining many different muscles and tissues and skin and other organs. And so it's a mixed sample. So it's getting blood, some of it's getting deoxygenated by muscles. The blood that goes to the skin doesn't really get deoxygenated, so it's pretty much fully oxygenated. And so you get this mixing of blood from all different sources. So that's why you could see the pressure of oxygen in the veins being higher than you would in the capillaries right at the muscle. All right, so there's a lot of benefits to this curve being not linear, not a line, but a curve. And it's that with hemoglobin having a high affinity for oxygen or wanting to hold on to oxygen at high pressures, like up here, that allows us to load oxygen on at the lungs where you have high pressures. And with hemoglobin having low affinity for oxygen when there's low pressures, that means that you're getting all the oxygen off of the hemoglobin, sending it out into the plasma so that it can be used. Okay, let's look at it in another way. So let's assume or just pretend that hemoglobin is like a bus, a school bus. Now, the point of a school bus is to pick up kids at the bus stop by their homes and deliver them to the school. So you want the kids to get on the bus at one spot, their homes, and get off at the school. So let's pretend that instead of this nice curve here, let's pretend that the relationship between PO2 and hemoglobin saturation was a straight line just up here. What would that mean? It would mean that we would get oxygen on the, we could be really good at getting oxygen onto the hemoglobin, but when it came time to get the oxygen off, when we got down to the muscle, we couldn't get it off. That'd be kind of like getting a bus driver that's really good at getting the kids onto the bus, picking them up at the bus stop. But then when it comes time to drop them off at school, they don't let them off the bus, right? You want to let the oxygen off of the hemoglobin. So that's one of the benefits of not having a straight horizontal line for the relationship. And then, as I've mentioned in the past, a reason for it being this curve means that we're good we're not super sensitive to the pressures at the top. So if the line just went like this, um, what this would mean if it's just a straight line, if we have a little less fewer kids one day, then we would get a lot less onto the bus. We wouldn't fill all the seats. If we have slightly less oxygen because we're going to altitude, we would have substantially less oxygen loading onto the hemoglobin at the level of the lungs. And that could be detrimental. But because we have this plateau here in reality at the end, we're a little more robust against changes in pressure at the level of the lungs so that we can fully load the hemoglobin if there isn't as much oxygen, and we'll have just a little effect on our on how much oxygen we're carrying for a small change in pressure than we would if it was a linear relationship here. So remember, the point of hemoglobin isn't just to carry oxygen, but it's to deliver it to the muscle. And if it doesn't let go of the oxygen, that's a problem, right? So that's why we have to have this change in affinity for hemoglobin for oxygen. At low pressures, it's more than willing to get rid of the oxygen and deliver it into plasma so it can be used. All right, that's what we'll end at for today. We'll talk more about this in person and during class.